All right, so here is an example for Kepler's third law. We have Titan, the largest moon of Saturn, has a mean orbital radius of 1.22 times 10 to the ninth meters. The orbital period of Titan is 15.95 days. Hyperion, another moon of Saturn, orbits at a mean radius of 1.48 times 10 to the ninth meters. Use Kepler's third law of planetary motion to predict the orbital period of Hyperion in days. So we want to know the period of Hyperion. Now let's write down our givens first. So we have the mean orbital radius of Titan. So I'm just going to put R sub T, as in Titan, is equal to 1.22 times 10 to the ninth meters. And then they give us that the orbital period of Titan is 15.95 days. So period of Titan is 15.95 days. And then we have Hyperion, another moon of Saturn, orbits at a mean radius of R Hyperion equal to 1.48 times 10 to the ninth meters. And it says use Kepler's third law, and we want to find the orbital period of Hyperion in days. Now, usually in physics problems, we want period in seconds. You guys have seen that when we have, velocity equals 2 pi r over period, and you're finding a velocity in, say, meters per second or something like that. Now, in this case, since we have the Kepler's law equation, which is kind of you're setting, your period squared over r cubed equal to another period squared over r cubed, it doesn't really matter what unit period is in as long as it's consistent. So since we want the period of Hyperion in days, we don't have to convert the period of Titan to seconds because that's already in days. So that's what we're going to get our period in, okay? Because the meters will cancel out. So what we get here for Kepler's third law, I know that period squared over radius cubed will equal period, will equal period squared over r cubed for another planet that's orbiting the same central body. So in this case, our central body is Saturn. And so since Titan and Hyperion are both orbiting Saturn, they're going to have the same Kepler constant, which is in our case, period squared over radius cubed. You can also make this radius cubed over period squared equals to radius cubed over period squared. Same thing. It doesn't really matter. Okay. Now I'm going to make this one Titan, the first one, and then the second one will be Hyperion. And so we're solving for T Hyperion. So T, our period of Hyperion, is going to be equal to the square root of the period of Titan squared times the radius, or R, of Hyperion cubed divided by R Titan cubed. So here, plugging in our numbers, we get the square root of 15.95 days squared times RH, which is 1.48 times 10 to the ninth meters. And we're going to cube that and then divide that by RT, which is 1.22 times 10 to the ninth meters. Cubed. So we get 15.95 squared times 1.48 times 10 to the ninth raised to the third divided by 1.22 times 10 to the ninth raised to the third. And then I'm going to take the square root of that whole thing, and I end up getting that the period of Hyperion is 21.31 days. Another thing you want to ask yourself here is, does this answer make sense? So if we look at the R distance of Titan versus Hyperion, Hyperion is farther away from Saturn, which means that the period should be longer. So the period for Titan is 15.95 days. The period for Hyperion is 21.31 days. So this answer does make sense.